So the next speaker is Dr. Elizabeth Castillo Martinez. She is a Spanish chemist who is currently working as an associate professor in the Department of Inorganic Chemistry at Complutense University of Madrid. Her research is focused on developing new materials for sodium and potassium-ion batteries and designing new chemistries for low-cost energy storage and conversion applications. She finished her PhD at Complutense University in 2008. As a postdoc, she got research contracts and postdoctoral grants in Dallas and Cambridge University, where she was awarded a Marie Sklodowska-Curie postdoctoral fellowship. Along her research career, she has participated in more than 20 research projects in different areas, leading a research on time temperature indicators and wearable batteries at Nanotech Institute in Dallas, sodium-ion projects in Think Energy Gune, a research on MOFs and COFs for energy storage at Cambridge, and her recent work in the search of anodes for potassium-ion batteries. Since then, she has co-directed 3 PhD students and 2 more going on, and has supervised several master's and undergraduate students, as well as participated in communication and outreach activities, and in the organization of international meetings such as First Symposium in Sodium-Ion Batteries. As it is clear, she has always demonstrated creativity and excellent capacity to carry out original research wherever she was. So thank you, Elizabeth, for coming today. It is a pleasure having you.
Thank you very much for the kind introduction. And thank you, Jesus, and the organizers for inviting me to be part of the symposium. For me, a pleasure to be part of this, and thank you for a very nice talk. So what I'm going to be talking to you about today is about the next generation of batteries. And my idea is to give you a very general overview of all the different chemistries. I have to say before starting that the topic is very broad. The number of different chemistries that has been being developed is very, very vast, and I'm sure I will leave some unexplored areas. So, but I would like to give you like a general feeling of all the things that are going on, even if I will be talking very briefly about my own research. So let me just try to increase a little bit my volume. Yeah, and I'll just use the laser. Yeah, and I'll just start. So as a starting point, I would like to start by setting up what is a battery. You all know it's a device that converts chemical energy into electrical energy. And to show this, we can look at the example of the first battery that was invented by Volta more than 200 years ago. What happens is that an electrode from the anode, or electrons from the anode, travel through an external circuit to a cathode. In the case of Volta's battery, this where the cathode was copper, the anode were zinc this. And they are separated by a fabric which is soaked in salty water. The salty water acts as a ionic conductor for charge balance. So what is going to determine how much energy can we store in a battery? What determines this, there are 2 factors. The first factor is the energy difference between the energy levels of the electron on the anode and the energy levels that the electron is going to occupy on the cathode. This energy difference is called voltage difference and is one of the main aspects of a battery. So as you can imagine, batteries in which we have lithium, they have a very high, the electrons that are shared or that are released are in very high energy levels, and therefore batteries composed or batteries in which lithium metal is involved have very high voltage. The other parameter is the amount of electrons that you can release, since each electron that travels from the anode to the cathode will release this amount of energy. If we were to look at a voltage versus capacity plot, which is typically what we see when a battery is discharged, the total energy, that is energy density of this battery, would be the energy, the area under the core. So lithium is the lightest metal, and also I think it's the lightest solid at room temperature and pressure, and therefore even if it releases only one electron, it can release lots of electrons per unit of weight. Also quite a lot of electrons per unit of volume. So I think with these two terms, voltage difference and number of electrons, you can agree that you can understand why actually lithium-based batteries are dominating the portable electronics market. Can you hear me well? Sorry, is it too low? Should I speak fast, louder? I don't think. Let me see if I can increase my no, my. That's all I can do. Sorry. I will try to get closer to the microphone, or maybe I just need to move the microphone. Can you hear me better now? So this is the reason why lithium-ion batteries are all around us. And actually, that's the reason why you all have lithium-ion batteries in your cell phone and in your laptop. But the importance of this invention, actually on the invention of the lithium-ion batteries that power our electronic devices, was recognized actually with the Nobel Prize of Chemistry in 2019, which was awarded to Professor John Bannister Goodenough from the University of Texas at Dallas, Professor Stanley Whittingham from Binghamton University in the state of New York, and Dr. Akira Yoshino for their development of the lithium-ion battery that led to their commercialization by Sony in 1991. So if we were to look at at a plot of energy density, volumetric energy density in watt-hours per liter versus gravimetric energy density in watt-hours per kilogram, it is clear that lithium metal-based batteries are in the top right corner. However, lithium metal-based batteries are unsafe so far, and that's why our batteries, our nowadays batteries, are mostly based on lithium ions, but do not contain lithium. If we see how the energy density of commercial 80 millimeter in diameter, 650 millimeter in height cells, these cylindrical cells, has evolved during their 30 years of their commercialization, we can see that both gravimetric and volumetric energy density has increased maybe by threefold. And this increase in battery performance is due to both changes in the chemistry of the batteries as well as changes in the engineering aspect. So if we were to look at one of these cylindrical batteries from inside, we will see that they are actually consist of a roll of many thin films stacked one on top of each. These thin films will be a cathode, a copper anode current collector, then the active material, the anode itself, which in the case of commercial lithium-ion batteries is graphite intercalated with lithium, then a polymeric separator, which has a microporous structure, and it's designed so that if the temperature rises because of some short circuit event, the pores close, and then the short circuit can be stopped. Then the layer of cathode material, which in the first commercial ion batteries, it was lithium cobalt oxide, and then the aluminum current collector on the cathode. As you can see, both the anode material and the cathode material have a layer structure, and they have capacities about 370 milliamp hour per gram and 140 milliamp hour per gram. You don't need to remember these numbers, of course, but this is to give you an idea, as I will be talking to you about other values for other materials that have been developed. And what is important is that the voltage difference at which the reaction, the redox reaction, takes place on both the cathode and the anode is quite large, about 4 volts approximately. But the development of these batteries had other issues to be solved. So if you were to actually, these batteries, we said that they had an electrolyte in which ions move. And actually for lithium-ion batteries, this electrolyte is composed of lithium salt, lithium perchlorate, or lithium hexafluoroarsenate, or lithium hexafluorophosphate, the most common case, in a mixture of carbonate solvents, propylene carbonate or propylene ethylene. What you can see here is that this electrolyte is actually thermodynamically unstable in the presence at the very low voltages at which is integrated into graphite, and therefore there is a continuous decomposition of electrolyte. The addition of ethylene carbonate to the electrolyte mixture, what makes is to promotes the formation of a passivation layer on top of the material that allows the voltage to continue going down and the lithium ions to insert into graphite, and this becomes reversible. So it is the formation of this passivation layer has become a very important issue in batteries. It depends a lot on the chemistry of the electrolyte, and it depends a lot on the chemistry of the electrode material. And depending on this, you will have a layer which has like a kind of polymeric matrix with inclusions of inorganic salts. And depending on the thickness of this layer, you will have more or less resistance, because this layer must be electronically insulating, but it must be ionically conducting. So actually, the lithium ions can still go inside and outside of the electrode. So this is a very important and active area of research. Every time any new chemistry is developed, especially this high energy density alkali and alkaline earth chemistry. But as you can imagine, after the development of these commercial batteries, research didn't stop, but on the contrary, there was a lot of activity. And from the layer structured lithium cobalt oxide, there was a movement towards more sustainable cathode material. So instead of using cobalt, which is mined in Congo mostly and in not very humanitarian conditions, let's say, other materials composed of manganese or iron as the transition metal, which are much more abundant and sustainable, has been developed. The lithium manganese spinel was developed as well in Professor Goodenough laboratory at Oxford and with his postdoc Mike Sakurai. And this crystal structure has three-dimensional tunnels for lithium-ion diffusion. This higher dimensionality with respect to the layer oxides gives this material higher power and allows it to be used for applications where higher power is required. On the other hand, the even more friendly lithium iron phosphate, which was developed also by the group of Professor Goodenough, but this time at the University of Texas and Austin, it has an olivine type structure where only one-dimensional tunnels for lithium-ion diffusions are there. This imposes some more limitations on the material, both ionic and electronic conductivity, but this can be overcome by properly nanostructuring the particles so that the tunnels where the lithium ions has to diffuse are along the short direction in platelet-like particles, and also by carbon coating the nanoparticles. In fact, this material is very much wanted for some applications like electric vehicle, because it doesn't have some of the issues associated to possible oxygen release that can occur in oxides. Given the fact that in a polyanionic compound, such as phosphates, the covalent phosphorus oxygen bond holds the oxygen atoms much more strongly in the structure. And if there is overpotential in the cathode during the charge of the battery, the oxygen ions are still very well attached. However, we still want to go towards higher energy density cathodes and anodes, and actually research activity on this area has been very intense. Starting from the lithium cobalt oxide, replacing cobalt by nickel led to higher capacity, because in lithium cobalt oxide, only half of the lithium ions could be reversibly extracted. With nickel, you can achieve larger amount of extraction. However, they have a high reactivity towards the electrolyte and also high thermal reactivity. So strategies involving doping, such as cobalt that avoids lithium with nickel mixing that occurs in the pure composition, or doping with some electrochemically inactive elements such as aluminium 3+, allows to have materials with high rate. Actually, this composition is used in many commercial batteries, and you will hear of it as NCA. The other composition that has scoped the market as well is the NMC, or nickel, manganese, and cobalt, wherein manganese replaces aluminum which is also another low-cost and thermally stable material. And actually, for this composition, the technology that has been developed and that is mostly used is a technology based on a gradient of composition of spherical secondary particles. So the material synthesized having a gradient of composition, so pure nickel phase, I mean doped with cobalt to avoid the anti-side disorder, is formed at the core of the particles, but there is a continuous gradient in composition as you go towards the outer surface, and the composition becomes manganese-rich to avoid reactivity with the electrolyte. And this gives a material with a capacity of about 250 milliamp hour per gram, which is quite high compared to the 140 of the lithium cobalt oxide. Another strategy that is being investigated is the use of lithium excess layer material. This material, and actually what I'm going to be talking about from this point, are materials which are not in commercial batteries yet. The 5 materials I talk about are the materials that make it batteries for the time being. But these materials have a lithium to transition metal ratio, which is larger than 1. This means that in one interlayer of between oxygen lattices, you have only lithium, but in the other layer, you have a mixture of lithium and manganese. Surprisingly enough, this gives capacities which are above the capacities of the NMC compositions, and also a very large plateau on the first chart above at about 4.6 volts versus. And there is a lot of discussion about this, and it seems that the most agreed argument is that the high capacity is likely due to an ion redox on the oxygen sublattice. But this is an issue because the oxygen can evolve. And although in the bulk of the particle, the oxygen is not released, it just reacts kind of reversibly. In the surface of the particle, there is some oxygen loss, I mean, an ion redox. And this leads to transition metal rearrangement. And because there is a transition metal rearrangement, the voltage of reaction. So what is observed in these materials is that the capacity, the discharge capacity, as well as the average discharge voltage goes down as we are cycling. So despite these materials have very high capacity, they still have some issues that keeps them far from. Other type of materials that has called lots of attention are those materials based on conversion reactions. They can insert also more than 1 lithium ion per transition metal, but in this case, all of the reactivity is due to the transition metal, to the redox properties of the transition. Here you can see a plot in which in 1980s already, the insertion of up to 4 lithium atoms in lithium iron oxide, in the layer lithium iron oxide, takes place. And if we look at the chemical formula, we can actually see that here the iron oxidation state is 0. And what happens is that we actually have iron 0 and lithium oxide. So although this type of reaction was known from the 80s, and it was reported for many oxides, nitrides, and sulfides, it was not until 2001, sorry, my slide is until 2001 that high cyclability was reported at room temperature for nanosite, cobalt oxide, and both the rock salt and the spin crystalline structure. And what is found in the room temperature cyclability is that actually the first discharge plateau is quite different from the following cycles. And this is because actually the structure that is cycled in the first cycle is different from that of the following cycle. Indeed, during the first discharge, what is proposed to be formed is that metal nanoparticles are formed within a matrix of the oxide or nitride or sulfide of lithium. And with also some phases from the electrolyte decomposition. Moreover, what is seen is that there is some additional capacity to that expected for the insertion of 1 or 2 or 3 lithium ions. And this has been assigned to some interfacial storage on the surface of the metallic nanoparticles, as well as to some possible further reactivity of the decomposition products of it. So although using these materials with huge gravimetric capacities would be very desirable, the large hysteresis and large first cycle Coulombic inefficiencies prevent them from going to market. Still, the mechanisms of reaction are still being explored. And indeed, for example, for the iron difluoride, rutile iron difluoride, it's been recently discovered that actually the reaction taking place is not just a pure conversion reaction where all the iron fluorine bonds are broken and new lithium fluoride bonds form, but by a study from PDF. Let's see if I can play the video. No? Well, there is a video here. Yeah. Well, that shows by using a non-matrix factorization algorithm, a new phase appears, and this phase can be modeled very well as a lithium-2 iron tetrafluoride. And actually, this phase is thought to be an interfacial structure which is formed to accommodate the very large structural rearrangement between the iron difluoride and the lithium fluoride. But actually, this phase can be coherently linked to both initial and final phases and seems to buffer the large lattice expansion and contractions between phases. So instead of explaining this reactivity with a one-step conversion reaction, we could explain this reaction as a two-step displacement reaction where lithium ions displace iron from the sublattice, and then the insertion of further lithium ions can completely extrude the total amount of iron. On the anode side, there has been lots of reports as well on trying to use high-capacity anodes. Remember that graphite has about 370 milliamp hours per gram based on the insertion of 1 lithium ion per 6 carbon atoms. But when lithium reacts with group P elements like silicon, aluminum, tin, germanium, lead, it can react through alloying reactions, which can give much higher capacities. For example, in the case of lithium, it can form lithium Si4, which has a capacity which is 10 times that of graphite. However, as you can imagine, if almost 4 lithium atoms per silicon atom enter into the structure, there is a large volume expansion with cracking of the particles, and after many cycles, these particles get completely pulverized. Not only this happens to each individual particle, but also the SEI layer that forms on top of the particles during the decomposition of the electrolyte in the first discharge also get broken. And in the subsequent cycles, new SEI layer needs to form on the surface of the new particle. Therefore, a very thick SEI layer that then prevents proper lithium-ion diffusion gets to be formed. Many strategies have been developed to try to overcome this, like compositing nanoparticles instead of micron size with carbon materials, putting silicon nanoparticles in a silicon oxide matrix that can buffer the volume expansion, as well as using different types of binders, which could be electronically conducting, and branch polymers, which can have a better addition to the silicon particle. Indeed, silicon is being used for some demonstration. I think it's not yet in the market, but many battery manufacturers are introducing, if not 100% silicon, a certain amount of silicon in their anode formulation. But still, the ultimate anode will be lithium metal. I mean, of course, we will have higher capacity with lithium metal than with silicon. And higher energy density batteries based on lithium metal instead of the rocking chair principle where the lithium ion moves from one electrode to the other could be a way to have higher energy density. However, let's remember that, I don't know if I told you at the beginning, but lithium metal was indeed in the first rechargeable lithium-ion batteries. Actually, Professor Bittingham, who proposed the lithium titanium disulfide battery in the 1970s while he was working at ExxonMobil, they commercialized their batteries with the lithium aluminum alloy anode, as well as Moly Energy commercialized as well lithium molybdenum disulfide batteries. And they had to withdraw their batteries from the market very fast because there were always problems of source circuit. And this is because of the dendritic growth of the lithium ion. I'm going to show you another video if I can, in which we can see, I hope you can see, we can see how lithium, when the battery is discharged and lithium is plated, supposed to be plated on the lithium electrode. I can't show you the video. I wanted to show you a video where you can see, but you can find it in this reference if you are interested, where you can see that sorry. Yeah, I'll move on. Yeah, so what lithium does, instead of forming a homogeneous thin film, it does grow in a very unhomogeneous way, forming like dendrites. And these dendrites tend to grow towards the opposite electrode, and sometimes they cross the separator and reach an source circuiting event. Oh, here it is. You can see the unhomogeneous growth, okay, while we are going down in voltage just towards lithium 0 volts. So if we want to make batteries for electric vehicles, which is one of nowadays concerns, I think nowadays we need to make better batteries for electric vehicles and better batteries for large-scale stationary applications. So if we want to make batteries for electric vehicle, we need to get rid of the flammable electrolyte that we have in our current battery. Lithium PF6 in ethylene carbonate, propylene carbonate, when the battery is short-circuited, it heats up and it can lead to explosion. So we want to get rid of the flammable electrolyte, which also in contact with air can form HF, and also if heated up can form some organofluoro compounds, which are not very nice for our health. So what can we do? We can use, instead of a flammable electrolyte, we can use solid electrolytes. And here there has been different strategies. One of them has been the use of a polymeric electrolyte, which actually was proposed by Professor Michel Arman already in 1987, where he proposed a rocking chair battery made of the cathode and a graphite anode. And to make the contact between the cathode and the polymer electrolyte with less interfacial resistance and to help the lithium ion charge transfer, typically the polymer electrolyte and the cathode are mixed on the cathode side. There is, of course, then a layer of polymer electrolyte free from the cathode. And the good thing of this polymer electrolyte is that there is no decomposition, so no SEA layer formation. Actually, these polymeric batteries, together with the lithium iron phosphate, has gone into commercial batteries, and it is used in the blue car that's running in Paris since 2011, as well as in the blue bus that is running in Paris as well, 2005. Other strategies is to use ceramic electrolytes instead of polymers. We know that ceramics can also be a good ionic conductors. And indeed, the first sodium sulfur commercial battery made by the Ford Motor Company in 1967 contained a ceramic beta alumina electrolyte, which transferred the sodium ions from a molten sodium tank to a molten sulfur tank. And this was at temperatures of 300 amperes. Actually, it was in order to study the conductivity, the ionic conductivity of this beta alumina, that then Professor Bittingen took some insertion electrodes, which could have variable amounts of sodium into their cavities, and to do this measure, and somehow made this insertion chemistry, or started this insertion chemistry. Actually, beta alumina was also used at room temperature by Professor Michel Arman on a sodium battery with a graphite intercalation. And since these late 70s, actually, since this works from the not so late 70s, many lithium ion ceramic conductors, and mostly focus on lithium once the lithium ion battery is off, has been proposed. And this are based on the lithium superionic conductor structure, the perovskite lanthanum lithium titanate, as well as the garnets or the amorphous lipon gases and sulfides. If we were to look at a plot of ionic conductivity, well, this is the logarithm of the ionic conductivity versus the inverse of temperature, we can see that the liquid organic electrolyte has conductivities at room temperature, which are in the order of 10 to the minus 2 Siemens per meter. And actually, some of the sulfides that has been proposed to have similar conductivities as well. However, what is more striking, and this is quite recent, is that there are some lithium-rich or sodium-rich glass electrolytes as well, which are derived from the antiperovskite structure that show conductivities which are very comparable to those of the liquid electrolyte as well, and even higher than that of the sulfide. And in some sense, these materials are not as sensitive as sulfides, although they have to be treated with some care as well. This type of glass electrolyte additionally have a very large voltage stability windows of excess of 8 volts. You can see they don't decompose at 8 volts above lithium ion. And what is very important, they have very good wetting properties towards lithium ion, and they enable the reversible plating and stripping of lithium metal. Actually, they can be plated and stripped for more than 24,000 cycles in a lithium glass cell. And very interesting features are being shown by this glass electrolyte, which seems to be contributing also to the capacity of the materials. So when making batteries with a lithium metal and a cathode material, not only the capacity from the cathode and lithium materials are achieved, but it seems that there is an additional contribution coming from the electrochemical double layer capacitors that are formed on the surface of the electrode. And this is seen as an increase of the specific capacity with the number of cycles, which is actually very unusual and not really seen in most of usual lithium-ion battery materials. I mean, at least in conventional insertion, intercalation, or conversion. So if we could use lithium metal with some of these polymeric, ceramic, or glassy electrolyte, what would be the best cathode material? And although we've seen many inorganic oxides, which could be great oxides and polysulfides, polyphosphates, polyanionic compounds, sorry, phosphates and sulfides with as electrode, actually, in terms of capacity, we could even beat them with sulfur, elemental sulfur, and elemental oxygen. And that's what actually has been made. Their specific capacities for the formation of lithium sulfide and lithium peroxide are very large, more than 1,500 milliamp hour per gram. This is almost 10 times that of the largest capacity cathode material. But of course, these batteries also have some problems. For example, if we look at the lithium sulfur batteries, sulfur is very insulating, so you need to add a lot of conducting carbon. But also, once it starts being reduced, it starts forming polysulfides, which in the case of liquid electrolytes, dissolve this polysulfide. If these polysulfides are dissolved, they can travel through the electrolyte towards the lithium metal. You have a redox shuttle events, which result in low Coulombic efficiencies. I mean, the battery is getting self-discharged. And indeed, if you look at how the battery is discharged after 30 minutes of being charged, or after 1 week of being charged, you will see that the capacity, which is delivered, gets much lower because these batteries have issues with self-discharge. Of course, there is an intense research on lithium sulfur activities to alleviate issues, like putting protective layers, making composite, having the sulfur trap into some carbon nanostructures to avoid this polysulfide redox shuttle event. On the other hand, the lithium air batteries, which were first shown in 1996 by Professor Abraham, to have even higher redox voltage, I mean, very close to 3 volts, and similarly high theoretical capacities based on the weight of it. However, if we think that we are taking the oxygen from the atmosphere, we somehow have some infinite theoretical capacity. But actually, lithium in contact with oxygen is forming most of the times lithium peroxide. And this lithium peroxide is a solid that once in the battery, does contribute to the weight and to the volume of the battery. So the capacity is actually not infinite. If we were to compare the theoretical and practical specific energy and watt-hours per kilogram of different battery chemistries, we see that the lithium-air is by far the one that shows the largest capacity. But also, if we reduce the contribution from all the external components like casing, current collectors, the practical capacity is not that much. Nonetheless, the theoretical capacity approaches that of gasoline, and that's why lithium-air batteries are on the spotlight for making it into electric vehicles. Some issues related to this chemistry is that in the presence of liquid electrolyte, the previous example was with polymeric electrolyte. In the case of liquid electrolyte, there is electrolyte decomposition, and this reaction, of course, is not reversible. And also that the lithium peroxide is clogging the pores, and then when you want to discharge the battery, you want to bring the lithium peroxide back into oxygen, you have an issue because the electrons are coming from the carbon. And you start by reducing the lithium peroxide in contact with the carbon. So once this is all, oxidized, once this is all oxidized, the remaining lithium peroxide gets disconnected from the carbon, and therefore you have lots of dead weight, which is not reversible. So in this sense, what the main strategy has been to use redox mediators, which are soluble in the electrolyte, and actually, instead of reacting with the lithium peroxide particles in the region where they are in contact with the electrode, they do react with the bulk of the lithium peroxide in solution. And this proves to be a very big improvement in reversibly reacting this battery chemistry. So it is important that the redox mediator is soluble in the electrolyte, that it has an oxidation potential above the oxidation potential of the lithium peroxide that we want to oxidize, and of course that this reaction is very fast enough. A breakthrough in lithium-air batteries came in 2015 in the group of Professor Gray, when they used highly porous reduced graphene oxide electrodes, as well with a lithium iodide redox mediator and some unwanted amount of water, well, unwanted at the beginning, but then wanted and controlled, in which actually, instead of forming lithium peroxide, it formed lithium hydroxide. If we form lithium hydroxide, we are getting 4 electrons per oxygen molecule instead of 2 electrons, and the capacity can be increased further. And the presence of the lithium iodide redox mediator helps on decomposing as well the lithium hydroxide product as would be for the lithium peroxide. Interestingly, water is needed to form lithium hydroxide, but the lithium iodide is also needed to form lithium hydroxide, because lithium hydroxide catalyzes the decomposition products of the peroxide species. And in the absence of lithium peroxide, lithium iodide, it is lithium peroxide that forms. However, if there is lots of water, the water cluster traps the lithium iodide, and then it decreases its catalytic activity. So there is an optimum range in which an optimum water content that can be put into the electrolyte to have the desired lithium hydroxide reactivity with proper reversibility. This can be further seen in these photographs where different amounts of water were added to a solution of hydrogen peroxide, and some lithium iodide and DME were added. And when the amount of water was adequate, there was oxidation from the iodide to the triiodide, and therefore the solutions were colored. Still, even if this chemistry seems very promising, there are still some issues to solve. For example, this battery actually works with oxygen, not with air, and it is necessary to take also into account that you need to avoid CO2, you need to avoid some other atmospheric pollutants, as well as to avoid this redox mediator to travel from the cathode to the lithium metal. If we were to compare the lithium air batteries with other metal air batteries, we see that in principle, the specific energy for a lithium air battery based only on the weight of lithium and oxygen is much higher than for any other chemical. But if we calculate the specific energy based on the weight of the decomposition products, this lithium peroxide or sodium peroxide, then differences are not that large. And especially if we take into account that aluminum, magnesium, although they are thermodynamically unstable in water, they can form some passivation layer that allows them to operate. Actually, zinc air batteries are amongst the most studied metal air batteries and among the most developed batteries. And one of the most important challenges are to control the kinetics of the oxygen reduction reaction and the oxygen evolution reaction. So control over the catalyst and about the along the cathode architecture needs to be considered. So this will be what concerns car electric vehicle. What about large scale storage? Of course, the requirements for large scale storage are very different than those for electric vehicle. And here, the more important criteria is the sustainability. So even though lithium is relatively abundant, we can find, although it's kind of geographically located in some specific areas, like in South America or in Afghanistan. But I think every day there are more and more mining places. Actually, we have some mining place in Spain as well. But still, you can see that aluminum, calcium, sodium, magnesium, or potassium, any of these elements are at least 1,000 times more abundant than lithium. So I think if we want to make massive batteries for electrochemical energy storage connected to renewables, we need to go to this other chemistry: sodium, potassium, magnesium, calcium, or aluminum. It is not only this element that needs to be considered. Of course, we also need to consider the methods of synthesis of the electrode materials and their recyclability and their processing. But one of the concerns is, of course, the use of lithium, as well as the use of cobalt, which I think it should be completely forgotten for stationary applications. So sodium and potassium ion, which are monovalent as well as lithium ion, do share in principle most of the same principles of operation of rechargeable lithium ion. And indeed, many of the processing parameters, like particle processing, how to make secondary particles, the composition of the laminates, that where besides the active material you have a conducting carbon and you have a binder, the additives that are used in the electrolyte for the formation of the solid electrolyte interface, many of these parameters can be transferred from the lithium and sodium ion battery to the, from the lithium ion battery to the sodium and potassium ion battery. However, actually, each of these chemistries has its specific issues. I mean, they are different. The abundance we've seen is 1,000 times more than lithium, but also the ionic radii change and its reactivity as well. One of the most important things is that, for example, sodium does not intercalate into graphite, which has been until now the most popular anode material for commercial lithium-ion batteries. You can see in this plot the discharge and charge in the insertion and the insertion of lithium ions into graphite. And here, in very small, in dashed line, you can see the insertion and the insertion of sodium ions has almost no capacity. And actually, this makes sense because the voltage for sodium plating is about 0.3 volts above that of lithium. And therefore, sodium will plate before lithium could be intercalated. However, it is possible to intercalate sodium ions with co-intercalated with some solvent molecules. at higher voltages, but as well at lower capacity. But interestingly, this co-intercalation does occur at a relatively fast rate. The fact that graphite doesn't intercalate sodium ions has motivated lots of research to search for alternative anode materials. And I'm going to show you an example of my own research here, where we prepare polymeric bases and propose them as electrode materials. And actually, we saw that the redox processes, two redox processes, which change in voltage with the change of substituents, of course, do take place at voltages close to 1 versus sodium plating. And therefore, it's interesting for anode material for sodium ion batteries. We could also go to lower voltages if we hybridize these SIF-based units with carboxylates, or we could even make self-binding thin film by copolymerizing the SIF-based functionality with polyethylene oxide unit. These materials actually have relatively good performance, although if we look at this plot of specific energy, considering the weight of the anode and cathode material, for a positive electrode composed of a layered sodium oxide by the British company Faradion, give us the different, taking into account the specific capacity of each anode material and the voltage at which the reaction takes place, which is indicated by these dashed lines, we can see which is the specific energy of the system. And we can see that actually sodium-ion batteries do have a slightly lower energy and specific energy than lithium-ion batteries, but they have other advantages, such as you can use an aluminum current collector in both electrodes instead of having to use the copper current collector that is in the lithium anode, because sodium as well as potassium do not form alloys with aluminium, and therefore you don't need to use copper. And aluminium is lighter than copper. Tin-based anodes and phosphorus-based anodes do have very large capacities because they are mostly based on the alloying reaction, and therefore they do have the issues related to pulverization and large volume expansion of alloys material. And hard carbons are actually the alternative that is being used in the initial commercial sodium-ion battery. On the other hand, if we look at the cathodes, we can see here in yellow the volumetric and energy density and capacity of lithium layer oxides, as well as many different sodium cathode materials. We can see that for layer oxides, we have many more compositions than for lithium ion, and this is due to the fact that you can de-intercalate sodium ions from layer oxides of many more transition metals, not only cobalt and nickel. Also, polyanionic compounds, phosphates and fluorophosphates have been tested, as well as some hexacyanometallate or Prussian blue-based materials, which on the other hand have lower volumetric energy densities, therefore do not appear in this plot. But it is the layer oxide that have the highest volumetric energy density, and the hard carbons has the highest energy. If we move from sodium to potassium, we can see that potassium ion does plate at voltages which are even below lithium plating, and therefore, in principle, one could even achieve voltages higher than those of lithium batteries. However, of course, there is a penalty on the weight of the potassium ion for the gravimetric energy density, and most of all, the main concern is that actually potassium metal is quite reactive, and we want to avoid potassium plating. And therefore, even though the voltage is lower, we will look for anode materials which are not very low in voltage or very close to potassium. Nonetheless, many people are looking into safely plating potassium, as this appears as a possible high energy density battery. For potassium-ion batteries, the Prussian blue materials are the preferred cathodes because their tunnel size perfectly matches the size of the solvated potassium ions. And you can see that the voltage is quite higher than that. The voltage of insertion of potassium ions is higher than the voltage of insertion of sodium ions in the same site. For the anodes, graphite do show a 60% volumetric expansion when potassium is intercalated into graphite. It's quite large, and therefore it is also interesting, and this is one of my current research areas, to look for alternative anode materials for potassium ion batteries. Nonetheless, it can be seen that by changing the binder from typical PVDF to polyacrylonitrile, the first cycle Coulombic efficiency can be reasonable. I mean, 80% is a reasonable value for a first cycle, and the capacity can keep some stability. So when investigating new anode materials, it's quite important to run in parallel the research of the electrolyte and the binder combination. So So what is beyond lithium, beyond sodium and potassium ion? We have the multivalent chemistries. We've seen already they are all very abundant, and magnesium and calcium, specifically calcium, has a voltage of reaction which are very close to those of sodium and potassium. However, both of these chemistries, I mean, magnesium intercalation was investigated earlier, but calcium ion batteries has started to be explored more recently, and they do not have larger specific capacities, but actually because they can exchange 2 electrons or 3 in the case of aluminum, the volumetric energy densities are even higher than that of lithium-ion batteries. An additional advantage is that when these metals are plated, dendrites are not formed. The main difficulty, however, is to find a good electrolyte that allows the plating, because we have cations with very large charge densities. I mean, we have a charge of +2. They tend to form ion pairs with their anions in the electrolyte, and also they tend to get very large solvations there. So it is quite complicated for the charge transfer to take place. So the strategies that are being used are to use high temperature, use large delocalized cations, as well as the use of ether-based solvents rather than carbonate solvents. Another issue with these multivalent chemistries is that it's difficult for the cation also to be inserted and extracted from a cathode host. Indeed, softer anions, such as sulfides, are preferred for the cathode material rather than oxides. And for magnesium batteries, it's the Chevreul phase, the molybdenum sulfide phase, which has shown the best performance, although the magnesium diffusion barriers are not very large in some sulfides and selenites as well. But for calcium, the best performance achieved so far is with titanium disulfide, and this takes place at very high temperatures and still relatively low C rates. So there is a lot of progress still to be made for these technologies to reach actually the market. The final multivalent chemistry will be that of aluminum batteries. Aluminum exchanges 3 electrons when it is electrodeposited or already solved, but it will have even more problems than calcium gas or magnesium gas to be intercalated into graphite. So the strategy to use electrolytes in which the aluminum ion gets coordinated by chloride anions, and actually what is intercalated is a single charge anion, the aluminum tetrachloride, that can be intercalated and intercalated relatively. So it is possible to achieve reversible cycling during 200 cycles and even more during thousands of cycles of this aluminum graphite battery. And to end, I would like to talk about another type of battery, which is quite different from all the batteries I've been talking about, and these are redox flow batteries. Very different from the previous chemistries is that instead of having solid electrodes where the ions get in and out and the electrons get in and out, we have the redox active species are dissolved in a solvent, so they are stored into tanks, and they go through the current collector to suffer the redox reaction. So redox flow batteries can uncouple energy and power because the energy density is determined by the size of your tank, whereas the power is determined by the size of your electrode. And the current chemistries in lithium in redox flow batteries are vanadium, which is the most popular, in which you have vanadium 2, vanadium 3 redox couple in the anolyte, and vanadium 4, vanadium 5 in the catholyte. Having the same chemical species is an advantage because you have a type of kind of symmetric battery where cross-contamination doesn't get such a big issue. Still, these aqueous suspensions have quite a low pH as they are in concentrated sulfuric acid. The other chemistry that dominates redox flow batteries is that of zinc bromide that reaches very large solubilities up to 8 mol. Of course, the larger the solubility, the larger the energy density of the chemistry. So increased solubility is one of the most important aspects in redox flow batteries. And then having a large voltage difference between the reactions that occur in both elements. But all these chemistries have corrosion, cost, and toxicity uses. So if we are going to make very large batteries for large-scale stationary applications, we want to move to more sustainable chemistries. And in 2014, actually, an example using anthraquinones, which are organic materials, very sustainable, made from biomass, where you can tune the redox voltage by changing the groups, was proposed. After this work, actually, in the last few years, many different anolytes and catholytes have been proposed, both in acidic, basic pH, as well as neutral pH. And it's opening quite a broad range of possibilities for the development of very large redox flow battery installation. Myself, I was involved in developing symmetric redox flow aqueous batteries, in which we were using dyes, which we functionalized to get a species that could be both oxidized and reduced, and therefore would enable to be used again in a symmetric battery, with all the advantages that I've already discussed in terms of minimizing the issues with cross-contamination through the membrane. Still, although these materials seem to perform quite well and we reach solubilities of up to 2 mol for some cases, there are still some issues related to how the solubility changes when you go to the reduce or to the oxidize or to the reduce. And this symmetric battery is just one of the redox flow battery configurations. The most common for the vanadium flow is with an ion exchange membrane. And in the fact that we have a symmetric battery, we could use a porous separator instead of an expensive ion exchange membrane. Also, if we have polymeric electrolytes, we can also have a size separator, which will bring down the cost of the battery. And I think one of the ultimate configurations will be a membraneless redox flow battery, where the two electrolytes do not mix because of immiscibility. And therefore, you avoid also some of the issues related to cross resistance, to large resistance between the membrane. So, in summary, I think I hope I've given you an overview on the current status of lithium-ion batteries, what the next generation of lithium-ion batteries could be with high energy density materials and solid-state lithium metal batteries, specifically for electric vehicle application, and what will be the next generation of more sustainable lithium-free batteries, which will depend on high energy density, sodium, magnesium, or calcium metal batteries, or even closer to the market, I will see sodium ion or potassium ion batteries, as well as redox flow batteries. It has been in the market for some years, specifically the vanadium redox flow battery. But we would like vanadium-free redox flow batteries to be developed. So I'd like to just say that, as I hope you have the idea that each chemistry has its own issues and there is not a perfect battery chemistry. And I would like to thank you all for your attention. And I would like just also some of my colleagues were part of the little things I show you from my research. If you have any questions, I'll be happy to answer. I hope I didn't get too long, a bit. I can't hear anything.
Yes, thank you so much for participating in this workshop, Dr. Elizabeth, and for this interesting talk. It's a pleasure to hear you talk about batteries. And if you don't mind, next move on to the questions. And to give time to the viewers, maybe I can start. So, how is the cost effective in potassium-ion batteries related to the potassium extraction? I mean, is the production of this type of batteries really profitable?
So, I mean, in this sense, of course, sodium-ion batteries are more cost profitable than potassium-ion batteries, because even if they have relatively similar abundance, you can extract very large amount of sodium from the sea. So in this sense, I think sodium-ion batteries are still beating. But still, potassium extraction is relatively simple, more than lithium extraction.
Okay. There is more comment. For example, there is a question from David regarding to versatility of sodium and promising potassium. How close are they to a former industrial application? Will they ever surpass the lithium ion?
Well, I think it's clear they will not surpass lithium ion in the sense of energy density. But as I said, I think the motivation for working with sodium or potassium ion battery is not reaching higher energy densities than lithium ion battery, but it's having a more sustainable system. And maybe we can keep the lithium for the high energy density batteries that we use for other applications. But I think the motivation is to have them for very large scale. Having said that, sodium-ion batteries do have already some commercial products. I think Faraday was one of the first companies already. I think it was already in 2015 when they brought their first battery to the market. I think I've lost connection for a bit. But potassium-ion batteries are still a little bit farther away. You also have to consider that research on sodium-ion batteries became very general about 2010. Although potassium-ion batteries were initially investigated when lithium-ion batteries, sodium-ion batteries were initially investigated when lithium-ion batteries in the 70s and 80s, but they were not. They didn't become the general research topic such as they are nowadays until 2010, when the interest grew up. But for potassium-ion batteries, I think it is now 3 or 4 years that is becoming quite popular topic. So they are still a little bit farther away.
Okay, thank you so much. Another question from Elena. You talk about sheaf bases as organic materials for anode applications, but wait, there is not the complete question here. So maybe I can read another one. Sorry, Elizabeth. Yes. Do they show lower stability than traditional inorganic materials, or would they be like to be used in large scale applications related to the?
This is interesting. I mean, of course, chip bases are prone to hydrolysis in contact with water. But this reactivity is not, they are not, at least the polymeric materials and the salts we have prepared, they don't show an extreme reactivity. And them outside and you can keep them vial. You don't need to have them in the glove box. But I have to say, we have not actually measured very long-term cyclability, if this is what the question refers, if it refers to their stability in the electrolyte. It seems stable, they seem stable, but we have not measured like thousands of cycles, only kind of focus on showing what are their initial electrochemical properties.
Thank you so much, Elizabeth. Another question from Cynthia Redondo. For measurements in a laboratory, do you consider that alkaline metals as reference electrodes are reliable, or can there be other alternatives?
Well, this is actually one of the issues with highly reactive alkaline metals. Yeah, they do, as you go down from lithium, sodium to potassium, reactivity increases, and actually lithium metal is quite good reference electrode, but sodium metal does show not to be a very good reference electrode. So it is always better to, I mean, you can use the lithium metal as a counter electrode and as a source of sodium, the sodium metal as a counter electrode and as a source of sodium, but it is better if you can, of course, use another electrode which has, for example, a flat voltage plateau, and get this material in the middle of this plateau to act as an electrode material. However, this electrode material, is a very good electronic conductor to have a good reference electrode. So it's not that easy. So what typically you can do is just to do the measurements in a 2-electrode configuration using the sodium or potassium metal as your counter and reference, and then do other measurements. If you want to have more precise control of the voltage, do measurements in a 3-electrode configuration where you use different sodium or potassium metal as current collector, where you build up a very large ACI layer because there is a lot of electrolyte decomposition, and then pressure sodium or potassium metal as a reference electrode. But still this is going to have some contribution from the electrolyte decomposition surface. So the preferred choice will be to use, as I mentioned at the beginning, metal electrode material in the middle of a plateau reaction, or just to use an external reference, like maybe a silver or a platinum wire, but careful with platinum to promote the composition of the electrolyte, but maybe a silver wire and some ferrocene to do it. But this is not very commonly done. I would think once you characterize your material in a 3-electrode cell, it is more common to then try to build a cell completely free of sodium or potassium, a 2-electrode cell against another cathode. If you're studying another material, against another cathode already well established.
Okay, thank you so much. And I think that we don't have much time for more questions. So thank you so much for participating, Elizabeth.
Thank you, Marta, for the questions. Thank you, everyone, for your attention.